This is video 2 for topic 9.1. Writing half equations. So when you're going to write a half equation, this is going to be separating out each of your reactants into what they're doing with the electrons. Remember, you need to have an equal number or a balanced number of electrons in each half equation. So if you're to add them back together into the full equation, they cancel out. But the purpose of the half equations is to see how many electrons are being transferred, because later when we actually talk about the purpose of redox reactions and creating what's called voltaic and electrochemical cells, which runs essentially your entire life at this point because everything is battery run and batteries are redox reactions, we need to understand what kind of movement and how many electrons are moving in order to create all the technology we have today. So here we have an example. So zinc is reacting with aqueous copper ions to create zinc ions and copper solid. So we want to go through and we want to figure out, what do these half reactions look like? First, we need to figure out who's being oxidized and who's being reduced. So assign your oxidation states first. Zinc is in its natural state, so it's going to be 0. Copper is an ion, so it's going to be the charge of that ion. Then zinc is an ion, so it's going to be the charge of its ion. And copper is natural state, so it's going to be 0. Going through and looking, so zinc goes from 0 to +2. It's becoming more positive, so it's losing electrons, therefore it's being oxidized. Copper is going from +2 to 0. It is gaining electrons, therefore it's being reduced. So now we know where to place electrons. So writing the half equation for zinc, so since zinc is being oxidized, it's losing, zinc is, we're going to write an arrow, and then we're going to write the ion zinc 2+, as we can see up in the full equation, plus how many electrons were transferred. So in order to identify that, go back and look at this little graphic we made, right? We go from 0 to +2. So that means we have 2 electrons being transferred. Copper is being reduced, which means it's gaining 2 electrons. So that means the electrons need to come before the arrow. And how many electrons do we write? Look at what we wrote over there, +2 to 0, so we have a transfer of 2. Now, they may not always be equal, and you'll have to go through and balance it. So the equation up here in this example is already balanced. Okay, so it's already balanced, therefore you don't have to worry about it. You can get an unbalanced one, and then you have to actually go through and figure out how many electrons, and then based off the how many electrons, go back and balance that equation. What's more difficult, what's going to take you some time, is writing redox equations from a half equation. So you're given half equations. Essentially, you're given 2 solutions. You're saying one solution, you have this half reaction, this solution, you have another half reaction, we're going to run a voltaic cell. And what is that full reaction going to look like? So that we can go through and analyze the data. First, you want to make sure it is balanced for your atoms and your charges. And then most reactions are actually going to occur in acidified solutions, which allows you to use H2O and H+ to help figure out and balance out your half reactions. And I'm going to show you what I mean by this. So here we have an example. NO3- reacts with Cu, and they react together in an acidic solution, and that allows us to know we're allowed to use water and hydrogen ions to form NO and Cu2+. So here we have our reactants. Here we have our products. Problem is, we don't know what the electrons are doing, where oxygens are going, so on and so forth. So what we're going to do is we're going to take this step by step. So first thing I want to do is draw a rough reaction of what's going on. Then I want to assign the oxidation states. So we know we have oxygen. There's 2 of them. 2 times 3 is -6. We need to make sure we still have a negative remaining. So nitrogen becomes +5. Copper is natural, so it's 0. Then over here, oxygen is -2. It's a neutral compound, so nitrogen becomes +2. Copper is an ion, so it's positive 2. So what's happening? Who's being oxidized? Who's being reduced? So nitrogen goes from +5 to +2. So it's becoming more negative. It is gaining electrons, therefore it's reduced. Copper is going from 0 to +2. So it is losing electrons, becoming more positive, and it's oxidized. Oxygen goes from -2 to -2. So we don't care about it. This is like a spectator ion, as we have seen in previous units on ions that don't actually partake in a reaction but are present just to be there to support it. Now that we have written and we have identified who's oxidized and who's reduced, we can move on from there. So I'm going to split them out into their rough half equations. So I have my atom who's going to be oxidized. That's copper. So we know copper is going from its neutral form to its ion form. And then who's being reduced? Okay, so we want to balance the atoms other than hydrogen and oxygen. Well, it's already balanced. So this one's a little bit easier. We don't need to do this step. Then we want to balance each half reaction for oxygen by adding H2O to the side that needs the oxygen. So our oxidation reaction doesn't need any oxygens because it's just copper. So our reduction, we have NO3 minus, so we have 3 oxygens on our reactant side. We have 1 oxygen on our product side. That means we need to add water to our product side. So we're going to add 2 waters so that we have 1 plus 2 equals 3. So now we have 3 oxygens on both sides. Then we want to balance each half reaction or half equation for hydrogen by adding H+. So going through our oxidation reaction, it is not applicable because again it's just copper. Our reduction, so we know we added NO3, we did NO3 minus. So if we go back and look above, we have hydrogen present on our product side now. So that means we need to add it to our reactant side. There's a total of 4 hydrogens. So I'm going to say NO3 minus plus 4H plus. That way they match. And it's balanced. And then we have NO plus 2H2O. And then we want to balance each half reaction for the charge by adding electrons to both sides, to the sides that have a more positive charge. So our oxidation, copper. So copper is more positive on its product side, which means that's where the electrons are going. It's being oxidized, so that means the electrons have to be in the product side. For our NO3, so then we have NO3 minus plus 4H plus. This is being reduced, so it's gaining electrons. But we don't know how many electrons. So let's go back and check real quickly. Okay, so if we know, and this was on a previous page, but we know we're going from +5 to +2. This difference right here is 3 electrons. So that's what we're going to write. Plus 3 electrons. And then our products. Okay? It's a lot of steps. And then really it just takes practice, and I apologize for what it is. It's just a lot. Once you have your electrons written down, you want to equalize the number of electrons that are being transferred. Okay? So if we look at our oxidation, copper transferred 2 electrons. Nitrogen transferred 3. The common value, therefore, is 6. So we want to multiply 3 across our entire equation in copper. So we get 3 coppers, makes 3 copper ions, plus 6 electrons. In our reduction reaction, we have to multiply it by 2, So then we have 2 NO3 negatives plus 8 hydrogens plus 6 electrons gives us 2 NOs and 4 H2Os. So these multiplication numbers multiply across everything in order to make sure we have the same number of electrons. So now we have 6 electrons on each side. Add your two half equations together and cancel out any commonalities. So taking a look at our half equations, the only thing that is common right now is our electrons. So those are going to cancel out because they're on opposite sides of the arrow. I did not do a good job doing this, but you may want to practice putting the arrows and aligning them so it's easier to see that, and I'll try to do that in the next example. All right, so writing out our full equation then, we have 3 coppers plus 2 NO3 negatives plus 8 hydrogens gives us 3 copper ions plus 2 NO plus 4 H2O. And that is the full reaction that takes place. It is complex, but that is what it looks like and why we have to do this process for an unknown solution. All right, I want to do one more practice with you guys just to walk through the set again. Okay, so if we have a reaction and we are reacting zinc plus sulfate, and that's going to give us zinc 2 plus SO2. First thing, assign oxidation numbers. So zinc is 0. Here, we know oxygen is -2. Times 4 is -8. We want 2 remaining, so this becomes +6. Here, zinc has a ion, so it's a +2. Then SO2, oxygen's -2. -2 times 2 is 4. +4 for the neutral compound. So let's identify who's being oxidized and who's being reduced. So zinc is going from 0 to +2. Sulfur is going from +6 to +4. And oxygen is going from -2 to -2. So zinc is becoming more positive, therefore it's being oxidized. Sulfur is going from more negative, so it's being reduced. And oxygen's just a spectator. Alrighty, so going through the steps. So zinc, we don't really have to worry about right now. So we're going from zinc to zinc 2 plus. All right, so that has no oxygens, that has no hydrogens, and it has no elements that need to be balanced. So right now zinc is good. So then let's look at the sulfate. Okay, so we have SO4 2- going to SO2. So this has some oxygens. We have 4 oxygens on the reactant side, 2 on the product side. So now we want to add water. We want to add 2 waters so that we have a total of 4 oxygens on both sides. Well, that means we need to add hydrogens, and we need to add 4 hydrogens to the reactant side to match it. And now we need to look at electrons. Okay, so zinc, if we go through and identify, zinc is going from 0 to +2, so we're seeing a transfer of 2 electrons. Sulfur is going from +6 to +4, so it is having a transfer of also 2 electrons. So that makes it easy. Electrons are already balanced, atoms are balanced. This is actually a very easy one, so cross out any commonalities. Do you guys see how I lined up my arrows so you can see the electrons are on the opposite side this time? It's a little bit cleaner. Then add it together. And it really does not matter how you write it together as long as everything's on the same correct side of the equation. And there you go. There's your full reaction.